Hi, we are trying to examine sequential circuit analysis. So we have done the analysis for more machine, which is this one, isn't it? We have already done it for this one. Now we came to the next frame, so we're going to repeat the analysis for the mealy machine. So there are some differences in the analysis between more and mealy machine. So therefore we are examining separately those two. So for mealy machine there are two examples here. The first example has less differences between the more machine. So therefore I am going to leave this one to do your own. In case you couldn't follow, you couldn't continue, or you couldn't find out the analysis, then you can watch my video, which is this video, about this mealy machine. So in this mealy machine, we are going to see all the differences between mealy machine and more machine. Therefore, you can examine this and then you can compare it with you can examine this video and the next video and you can compare it, and then you can do this mealy machine example your own. So we are going to examine the time diagram analysis of this mealy machine separate video. So there's going to be another video about this frame. And this frame is about the protos analysis. As you know, analysis is based on the three models: mathematical model, state diagram, and state table. Apart from those, how you could do the analysis, you could do the analysis, go to the lab, and set up your circuit on the breadboard. Then you could analyze your circuit there. That's another analysis that you could do. The fifth analysis is the Protos simulation program. You could analyze this mealy machine by using the Protos. So this Protos result is just for you to compare. There's not going to be any video on this Protos analysis, since you know the Protos already, so you can compare the results between the state diagram and the Protos. Okay, let's move to our example circuit now. Move this up and put that out port in and set up the OBS, open board. Okay, now we came to that point now. So this is the mealy machine example. Do we have the right to say this is a mealy machine or not? We've got to look at the output function. So look at this output function. Maybe I can show it. So that's the output function that we're going to consider. Now this output function, if it is the function of the state variable and also the input variables, then I'm going to say the mealy machine. So when I said these variables, I've got to determine the independent variables of this circuit first. What is the independent variable? Put it in green color. So this is an independent variable. That's the input variable. That's an external variable. Another independent variables are related to memory elements. Each memory element represents one state variable. A small y version of the state variable is the independent variable. So this small y1 and this small y2 are also my state variables. But capital Y1, capital Y2, these are not independent variables. You've got to pay attention to that. Then conclusion is this: in order to say whether this is a mealy machine or Moore machine, I've got to write out the Z output function, that function, in terms of independent variables. Now I am doing it. How I'm going to do it? By examining my circuit. Z is the output function. Go back here. This Y1 comes from here. That is X. X comes from that X. So in reality, there should have been a line up to here. So multiplication of those two, this is the AND gate. Output is going to be X, Y1. So for this AND gate, one of the input is Y2, the other input X prime. So the output of the AND gate X2 prime Y2. So summation of those two give me my Z function. That is X, Y1 plus X prime Y2. So that's my output function. So if you look at the output function, so you're going to see that this function is the function of the independent variables, state variables, also the input variables. Therefore, it is a mealy machine. If it were the function of the state variable only, then we were going to call it Moore machine. So I know it is a mealy machine now. So how I'm going to analyze the mealy machine, it is the similar way that I'm going to do the analysis with the Moore circuit analysis. So what are they? Find the three models. The first model is the mathematical model. The second model, state table. And the third is the state diagram. Why we are having three models in order to analyze the circuit? There is a reason, of course, for it. So I can repeat it once more here as we have done it in Moore machine. If your state has got a few memory elements and a few input variables, that we call it a simple circuit. If you are going to analyze your simple circuit manually, then the best analysis model is the state diagram. If you've got many memory elements and many input variables in your circuit, then the best model to analyze is the mathematical model. So normally, let's call this as a complex sequential circuit. When it is a complex sequential circuit, it's not reasonable to do it by hand. You're going to do it by using computer program. So in this computer program, this is the model to be used. Therefore, we are examining these models separately. So you might ask, what is this state table then? In order to transfer the mathematical model, the state diagram is the best way to draw the state table and then state diagram. Therefore, I need the state table as well. So let's start for the first one, the mathematical model. Mathematical model is to find out Y1, capital Y1, and capital 2 dependent variables, that means functions. Not in here, this capital Y1 and Y2 is not seen in the Z function. But we are going to find them out in this mathematical model. So the other dependent function that I'm going to find is the Z output function. So in order to find the next state functions, I've got to know the definition relation of my memory elements. What is the definition of the memory element? Let me draw it here. And JK memory element definition relation. So the other one is JK. And this one. Okay. D01, small y, 01. When the input is 0, output is 0. When the input is 1, output is 1. So this is capital Y equal to D. So for JK flip-flop 0 0 0 1 1 1 1 0, so the small y is 0 1. So definition is this: when it is 0 0, no change on states. So when the inputs are different, whatever J says is going to be observed at the output 0 0. When the input is 1 1, it toggles. That means if your present state is 0, next state becomes 1. If your present state is 1, your next state becomes 0. Toggle, that means. And when the 1 0 input applied, the J says is going to be observed at the output. So that is this. So if you write the mathematical function for this capital Y1, is this because of this 1 1, so you're going to have J times Y prime, J times Y prime plus this to 1, that means K prime times small y. So let's come back here. So Y1 is equal to D. When I write this function like this, this is not the function that I am looking for, but it is the beginning point. Because I said I'm going to write my dependent functions in terms of independent variables. So there is no independent variable here. My independent variables are these green ones, aren't they? This x, y1, and y2. So I'm going to transfer this d variable to these independent variables. How I am going to do it? Go back my circuit. If you look at d input here, this is OR gate x plus y1, and this is y2 input. So multiplication of those two gives you the end output of this AND gate. That means xy2 times y1 y2 plus y1 y2. So this is the function that I am looking for. This is the next state function because all these variables here are independent variables. So let's come to y2. Y2 definition relation is here j y prime to k prime y. So this small y in this must be the same as the next state function input index. So that is going to be 2 definitely, because this is related with the second memory element, isn't that? All the indices for the states are going to be the same. Okay, what is this? Once again, this is an independent variable. We accept that. But this j and k are not independent variables. So I've got to transfer these variables to my independent variables. How I'm going to do it? Look at the circuit. So j input is this, isn't it? What is the j input? Is exclusive for this input and this input. So I'll write it here: x exclusive or y1 prime times y2 prime plus k prime. K is equal x prime. Prime of x prime gives you x, so that's x times y2. So what is this? Is exclusive for? Use the definition of this one, and the prime the other one. So x prime the other one, prime of y1 prime gives you y1, so x y1 plus prime of this and this variable itself. So x prime y1 prime is my exclusive OR output. So I'm going to multiply this by y2 prime. So x y1 y2 prime plus x prime y1 prime y2 prime. I am multiplying this one with this one plus this product term here, x y2. So this is my second next state function. So I finished the mathematical model. Why is that? Because I have already defined this z output function here, that's the one, and the next state function y1 here, and next state function y2 is here. So that means this one and this one and this one. So once we finish the mathematical model, then we can find the state table easily. Let me draw the state table here. So my independent variables are y1, y2, 0, 0, 0, 1, 1, 1, 1, 0. Pay attention that this order is the kernel map order. Why I am writing it is in the kernel map order? Because I am going to transfer my three variable functions to this. When it is kernel map, it is easy to transfer these functions on this kernel map. That's why we are keeping the kernel map order here. So the third variable is x equal to 0 and 1. So inside I am going to write now y1 next state function, y2 next state function, and a comma z function. So that means I'm going to transfer all these mathematical model functions to this diagram. How I'm going to do it easy? Let's start from y1. This is x, y2. When this becomes 1, when x equal to 1 and y2 is equal to 1. X equal to 1 means this column. Y2 equals to 1 is this 2, isn't it? Y1 is changing the value, that's why it's going to disappear. So y1, this is 1, 1. So this 2, 1 represent this product term. So you can consider it in opposite way. While we are finding the minimal function, we were seeing these next to each other 1, 1. That means first order subcube. If it is the first order subcube, the value of a variable which is changing, that means this y1 changing the value, that's why that's going to disappear. When you move this away, what is left is x, y2, which is this. This is y1, y2, so y equal to 1, small y1 equal to 1 and small y2 equal to 1, that means that column, that row, isn't it? So if I put here, so these two 1 represent this product term. So since I considered all the product terms, that means the other cell values are going to be 0 for this capital Y1 next state function. So put 0, 0, 0, 0, 0 here. Okay. So let's transfer this y2 next state function to this diagram. How I'm going to do it, look at this product term. When x equal to 1, y1 equal to 1, and y2 equals 0, this product term becomes 1. So what is this? X equal to 1, this column. Y1 equal to 1 and y2 equal to 0 is this row. So if I put 1 here, this one corresponds this product term. The next product term is x value is 0, y value is 0, y2 value is 0. When you give these values, these variables, so this product term becomes 1. So that means your function becomes 1, isn't it? 1 plus anything gives you 1. So these values are x equal to 0, that column, and y1, y2, both of them 0 is this row, isn't it? So I'm going to put that one here. That one represents this product term. So what is left? This product term. This is x, y2. So the same as x, y2 here, isn't it? So x, y2 is in the first next state function and also in here. So this is x equal to 1, y2 equal to 1. So those two, isn't it? X equal to 1, y2 equal to 1. So you can check it that for y1, those two 1. Also for y2, those two 1. So when you consider all this, so these two ones represent this product term. So all the other cells values are going to be 0. So we finished next state function y1 and y2. What is left is z. So let's transfer this z to this diagram, put commas here. It says x, y1, x is this x equal to 1, this column, y1, those two. So I put 1, 1 here. These two represent this product term here. So let's say this product term here is represented these two ones. So z function I am writing. So the other one is x prime y2. X prime is this column, y2 value equals to 1 is this 2. So I put 1, 1 here. And we consider 3 product terms, the rest of them is going to be 0. So I transfer z output function to my state diagram as well. So I can say that z function, this product term is represented by these two ones here. So once you find the state table, then you can find the state diagram. State diagram is going to have 4 circles for each states. So we've got 2 state variables. That means we can represent 4 different states. So I'm going to put in a circle those states. That is 1, 2, 3, 4, 0, 0, 0, 1, 1, 1, let's say 1, 0, and 1, 1. So look at the first row here, present state 0, 0. If your input is 0, your next state is 0, 1. So it is like that, isn't it? If your input is 0, your output is 0, so it's like that. So let me repeat it once again. Present state 0, 0, your present state 0, 0. You apply input 0, you applied input 0. Your next state is 0, 1. Put that arrow here, is 0, 1, your next state. Your output z is equal to 0, so we write it here. So this is input, and this is output. So let me say the difference between Moore and mealy machine. If it is Moore machine, z output function depends on your present state independent variables. So you can write the z value underneath here. But in here I cannot write it because my z output function depends on the x variable as well. So for different inputs, I am going to get different outputs, z's. So that's why I put this on this arrow, input and output. On the state table, the differences was this. If we don't write the z function in these x columns, because z is independent from the x input, very independent variable, so I put z one separate column here. Since you don't know the present state, then you can write the z output function. So that's the difference between Moore and mealy machine when you are setting up state table or state diagram. So let's come to the next state now. My present state 0, 0. If my input is 1, my next state come back to itself. So that's going to be like that. Input 1, that input, and output is 0. Output is 0. So let's get the second row. Now my present state is 0, 1. That means I am in this state. if you apply 0, you go to 0, 0 state. So if you apply 0 here, 0, 1 state, present state, next state is 0, 0, next state, present state 0, 1, next state 0, 0, input 0, input 0, output 1, output 1. So if you apply 1 when your present state is 0, 1, your next state is 1, 1, isn't it? So it's going to be like that. For input 1, my output is 0. So this output 0 represents this. Okay. So we finished 0, 1 state. Let's come to 1, 1 state. 1, 1 state goes to 1, 0 state if your input is 0. So 1, 1 state goes to 1, 0 state if your input is 1. Your output is 1, isn't it? So this one here is this output. If your present state is 1, 1, if you apply 1, your next state is the same as the present state. So it comes back itself. Input 1, output 1. So the last one is 1, 0 state. 1, 0 state goes to 0, 0 state for input 0. So it's going to be like that. When input is 0, your next state is 0, 0. Your output is 0. So this 0 output is this 0 output. If your present state is 1, 0, if you apply 1, your next state is 0, 1. So it's going to be like that. So that means input is 1, your output is also 1. So let me read it once again. Your present state is 1, 0 here. So that's that 1, 0. If we apply 1, your next state is 0, 1. So your next state is 0, 1. Put that arrow in. Your input is x equal to 1, and your output is also 1. Right. So we found the state table as well right now. Now we can choose any input variable sequence, then find the output variable once we found the state diagram here. So let's assume we are applying 1, 1, 1, 1, 1, 0, 1. Let's apply this sequence. I chose this randomly. Now we are in a position that any input bit stream given to you, you can write the output bit stream. Any, I said. What it means, any length, any 0, 1 combination bit stream, you can find the output bit stream. So once you, so that is, the time goes like that. So this is our x, isn't it? So we've got to know also our initial state. Which initial state I'm going to apply this input. So you must give the initial state as well. So initial state, let's assume that 1, 1. So you can choose this randomly, of course. So if my present state is 1, 1, let me write it next to here, 1, 1. Make it a better way now. 1, 1 here, y1, 1, 1. So I'm going to write now z now. So I'm saying if you are on the state table, state diagram, so you can easily find it. How are you going to find it? Our present state is 1, 1. You're applying 1. So you're going to observe now. Let me make it different color. This one, isn't it, at the output. So that's the first output you're going to examine. So I said present state 1, 1. Your input is 1. So at the output you're going to observe this before the clock pulse, right? Why I said before the clock pulse? Because Z output is the output of a combinational circuit, isn't it? So if the input is known and present state is known, so you're going to observe one thing here, that is the Z output. So that means I'm going to observe this one. So, and then I am applying this second one here. So in order to separate the first and second, you're going to apply clock pulses for each of them. Now I haven't applied the clock pulse yet. So if you apply first clock pulse here, your next state is going to be 1, 1. So after the clock pulse, your next state is 1, 1. When you come to this 1, 1, so you are applying there's a mistake. Once again, I found a mistake. Where is that mistake? Is this, isn't it? Input 1, present state is 1, 1, that means you are here. If your input is 0, your next state is 1, 0. So if your input is 0, so that's going to be input is 0, isn't it? Input is 0, your present state is 1, 1, your next state is 1, 0, like that. Output is 1. Now when it is 1, it is true here. So we have done it. So my next state is 1, 1. So I am going to observe this one as I already said. So when the clock pulse comes, you are going to come here and you are applying one more clock pulse for this second one. So that means this one, you're going to observe this once again. So if you do it for the third time, so that means third time you're going to have this one, isn't it? Once again, you're going to observe the output third time, this output. So after the clock pulse, you come to this 1, 1, and you're going to apply the fourth clock pulse. Fourth clock pulse is 0. Fourth clock pulse applied when the input is 0. Your output is this one. So this is the fourth output here. So when the clock pulse comes, you're going to come to this next state. This next state, you're going to apply the fifth clock pulse 1. When you come to the next state, if your input is 1, your output is 1. So that's going to be the fifth one. Okay. Now let me write it next state as well. My present state was this at the beginning. And then for the first clock pulse, I am in here now. Beginning here. First clock pulse here. Second clock pulse here. The same next state, that is. And third clock pulse is 1 again, so once again here, fourth here as well. So my fifth next state is going to be this. And for this, when I apply this one, before this clock pulse comes, you're going to do this now. Why there are 6? Because if you consider the present state as well, for each clock pulse you are changing the states. For the present state there is no clock pulse. So altogether there are 6 changes for the states. For the input sequence is this. My output sequence as written here. 1, 1, 1, 1, and this one. So my output sequence is this. You see all of them 1. For this input sequence, if you change the input sequence, you could say that at the beginning I apply 0, so you go different path. So your initial state changes, then your output is going to change. So that means output changes with the input present states, the output sequence is changing. But if your input bit stream is 5 bits, so your output stream is going to be 5 bits as well. So that's the end of this video then.